Okay, guess we can go ahead and start the class. Your homework 2 is posted. It has a total of 11 questions on it, but the last one is a bonus question. So if you end up solving the last one, you will get 20% bonus. Not the homework, it will be 20% of the homework grade, but it will be added to your final grade, if that makes sense. Essentially, homework, I think homework is 4% of your total grade. So 20% of that homework is like 0.75% of the total grade eventually. Okay. So yeah, homework is posted. Make sure to check it out. It is on chapter 2, fluid statics, that we have covered so far. I try to give you as many questions as possible to make sure that you have practiced enough with the material. And it will be due on Thursday before the class, so 2:50. I created the assignment on Blackboard, so you don't need to bring a hard copy. You can just submit a PDF file on Blackboard, which is going to make, I think, everything easier for all of us. So please don't bring a hard copy in the class. Just submit everything on Blackboard, and we should be fine. I asked your grader to grade your homework ones as soon as possible. He is running behind. I make sure that your homeworks are graded before the next homework ones are graded before the next class, before Tuesday. Is there any questions? No. Okay, so let's continue the discussion. We are going to solve some more example problems on the topic of fluid statics. And then we'll move on to the chapter 3 next week, which will talk about the Bernoulli's equation. On Tuesday, we were talking about this problem. Yeah, the gate. Okay, and we wanted to find the moment, or we wanted to show that the moment in the clockwise direction, which is going to be positive, is equals to your density of water, gravitational acceleration, h multiplied by b. Yeah. This is h. This is b. And L squared over 2 minus h squared over 6. And we were able to calculate this moment. We first find the horizontal force, vertical force, and the moments they create around this hinge. And we essentially came to this final formula. But the rest of the problem is asking us, what is the counterclockwise moment that you need to have to open this gate? Or what is the total moment that you need to have? So as you can see from the figure here, if you have a clockwise moment or a positive moment, this is our sign convention, right? We assume a clockwise moment is positive, it will get stuck here, right? So a positive moment cannot open the gate. We need to have a negative total moment so the gate moves in this direction, right? So your sigma m has to be negative, or total sigma has to be in the counterclockwise direction. And keep in mind that this is our sign convention. We assume clockwise moments are positive, counterclockwise moments are negative. Okay, so we just have to find a condition for which total moments are smaller than 0, negative. We already have the equation. This equation has to be smaller than 0. These parts are always positive, they don't change. So the only part that we really can focus on is this part of the moment. L squared minus H2 divided by 6. Sorry. This part has to be smaller than 0, right? Because the rest of it is always positive. So positive has to be multiplied by a negative value here to become a total negative moment. Okay? And this is only true when H squared divided by 6 is larger than L squared divided by 2. Okay? Which essentially means if you move 6 to the other side, take the square root, this essentially means that your H has to be larger than a square root of 3 multiplied by L. So you have to fill out the water this much. It has to be, you have to fill it up until this height of the water becomes larger than a square root of 3 multiplied by, this is L. So multiplied by this length. And if you are, this B here, what's my mistake? This B here is the depth, if you will, right? In this direction. Width of the gate, or whatever you want to call it. Is there any questions? So if we want to open the gate, if we want the moment that the water is creating there, to open the gate, the moment has to be in the counterclockwise direction because it has to push the gate in this direction, which means that the total moments have to be negative. Plug all of those. We have the equation, and we can plug the equation here for moment, and then we can calculate the condition. Is there any questions? So let's solve another problem. The next problem, we are going to mostly focus on manometers again for the next problem. You actually have 2 or 3 questions from manometers in your homework, and you will definitely get a question on your exam as well, and in the final exam, in at least exam 1, right? So we have this manometer. Okay. We have pressure B here. We have PA here. The height of this column on the B side is H2. The height of this column on the A side is H1. Pressure inside here is 16.1 psi. The absolute PA and PB are equal. Is equal to 14. So that's one thing that you have to keep in mind, that we are not dealing with gauge pressure here anymore because we have the absolute atmospheric pressure, right? If you were to calculate the pressure, you're dealing with absolute pressures. Or if you can always calculate the gauge pressure and just mention that you have calculated the gauge pressure, right? You just have to make sure that you are clear on this. Okay, so we have this type of manometer, and we have 2 different situations. For part A, we want to calculate the height difference, H1 minus H2, when there is an air bubble here. That's for part A. We want to calculate the H1 minus H2. Okay, so what should we do? The first thing we need to do is to find, and the working fluid here is water. It doesn't really matter, but the point is the working fluid, everything, everywhere is the same. And we have a water bubble stuck here. Okay, to answer part A, one thing you need to find, that's the thing we always find, is a height, a reference height, right? Let's do this as the reference height because we measure every height from this reference point. So the pressure here and pressure here. Let's find the pressures here and pressure here. P1, P2. Okay. P1 is going to be equal, it's a hydrostatic pressure, so it's going to be equal to PA plus gamma of water, or rho g of water, H1, right? And P2 here is going to be PB plus gamma of water, H2. Well, what is the relationship between these two pressures? We have an air bubble stuck here. How is it going to change our problem, essentially, our pressures? To answer this question, you have to go back to the nature of hydrostatic pressures. The idea was it mainly depends on height or depth. So our main point here was that as long as you are dealing with the same fluid at the same height, your pressure doesn't change, okay? The pressure here is going to be the same as pressure here. Pressure here is going to be the same as pressure here. And since we are not assigning any thickness to this tube, we can just assume it's a line, it's a rod, which means that the pressure at the two sides of air bubble has to be equal as well, right? So pressure at this point, which is equal to pressure at this point, which is equal to pressure at this point, is going to be equal to pressure at this point. So P1 is going to be equal to P2, which means that PA plus gamma H1 is going to be equal to PB plus gamma H2. PA and P1 are equal. They are both atmospheric pressures. So we cancel each other out. Gamma of water is going to stay the same. And this is going to tell us that H1 is equals to H2. So H1 minus H2 for part A is 0. Okay. Is this clear? Okay. Let's do part B. Part B is telling us to find that height difference, H1 minus H2, when the air bubble moves here. How is this going to affect our calculation? Okay. So we have to follow the same idea here. We want to find the pressures at this point, P1 and P2 again. Since they are the same height and there is no air bubble here anymore, we can safely say without any dot, we can say that these two are equal, okay? P2 because they are at the same level, at the same height. P2 is PB plus gamma H2. Okay. Let's look at this column. What is the pressure at this point? Let's call it P star. What is the pressure at this point? It is PA plus P star, PA plus gamma, this height. Let's call it H star, right? And the pressure here, from here and here, let's call this pressure here, let's call it P star 1, right, instead of P star. The pressure difference between these two is going to be gamma, this H1 star, this height here, right? These two things we can say with confidence, right? But what is happening around the air bubble? What is happening around that air bubble? Let's go back to this discussion we had earlier. What is the forces? What are the forces, or what is the force that a fluid exerts to an object that is immersed in that fluid? What did we call that force? The buoyancy force, right? So we have an object, whatever object is that, the fluid exerts the buoyancy force to it. The buoyancy force was the weight of the replaced fluid, which was gamma of this fluid. If it's water, gamma multiplied by the volume. Okay. Can we say this air bubble is immersed inside this fluid? It looks the same. It is definitely immersed inside that fluid. So the force that fluid, the water, is exerting on in this air bubble is going to be gamma of water multiplied by the volume of this air bubble. But here we are assuming that it's a two-dimensional case and the pipes are very narrow, which means that this force is going to be reduced to gamma multiplied by H. But the force is being exerted in the opposite direction compared to the hydrostatic force. So what does it mean? It means that the pressure we have here, if we then have the air bubble, P1 would have been equal to PA plus gamma H1. Okay. But inside this column, we have an air bubble that the water is exerting a force on to push it upward, to push it up, right? It is in the other direction, in the opposite direction than the static force. So we need to include that as well. That's the, let's call that gamma H is going to be your buoyancy pressure, right? Not the buoyancy force. So the force divided by area, cross-sectional area, which is the unit area. So your P1 is going to be equal to PA plus gamma H1 minus H. Is this clear? So if we didn't have the air bubble, the pressure would have been P1. The presence of air bubble is essentially introducing a buoyancy force in the opposite direction. Okay? So these two, the pressure 1 and pressure 2 are equal. It's a little hard to read this. Are equal. I'm going to write it up here. So PA plus gamma H1 minus H. And this is the height. H is this height of the air bubble, right? In case I forgot to mention. PB plus gamma H2. These cancel out. They are the same. Gammas cancel out. So H1 minus H2 is going to be equals to H. So if you have an air bubble stuck in one of the vertical columns, then your height of that column that has the air bubble in it is going to be higher, right? How much higher? Length of the bubble higher. Is this clear? Okay. So let's move on to another example. So we have a above ground swimming pool. And this is the one of the walls of that above ground swimming pool. We of course have water here. And that's the free surface of the water. We have installed the plexiglass here. It's a semi it's actually called a hemisphere. Hemispherical. So it's half a sphere. Hemispherical shape thing, right? And it's made of glass in case you wanted to look inside the pool. It's an observation glass, right? The diameter of this glass is 2 feet. The window, this glass window is bolted onto this vertical wall of the pool. And the center of this glass is 4 feet deep. We want to determine the horizontal and vertical components of the force of water on the hemisphere. Horizontal and vertical force. So the first thing, whenever you're dealing with the forces, and I think we solved another example of this as well, but we didn't talk about it in class that much when we were doing the lectures. The first thing you do when you want to deal with a curved surface, right? When you want to find the forces on, is to do a free body diagram that covers the curve and the water inside that curve, and then write a free body diagram for it, like FBD. Let's say this is your glass, and this is the body of water that is inside the glass. What are the forces we have here? You have your weight, you have the horizontal force from the glass itself, you have the vertical force, and we also have a force that is being exerted by the rest of this water here. So the first thing you do whenever you are dealing with a curved surface is to write a free body diagram. The only difference between a curved surface and a regular surface is that you have forces. You have two components of force. That's it, a horizontal and a vertical. Okay. So, and since nothing is moving, sigma F in X and Y has to be 0. What does it mean? It means that your horizontal force has to be equal to Fr, and then your vertical force has to be equal your weight. How do we calculate the force of water here? That's essentially the hydrostatic pressure force on just a regular vertical wall, right? And we have already seen those. You essentially have to find the equivalent hydrostatic pressure multiplied by your gamma and then the cross-sectional area. I mean, the gamma is already included in hydrodynamics. Sorry. PC is multiplied by A in the pressure. And for weight, what do we do for weight? How do we calculate the weight of this body? It's your gamma multiplied by the volume, right? Rho G multiplied by the volume. Okay. What is the volume of this hemisphere? To answer that, you have to first know what is the volume of a sphere. Volume of a sphere is 4/3 pi r to the 3, right? Raised to the 3. If you recall, a volume of a hemisphere is going to be half of that, right? So, our volume here is going to be 4 to the 6. We have the radius, which is 1 feet. The diameter is 2 feet. The radius is going to be 1 feet. Plug the number in, should be good to go. And gamma of water it's usually given to us in problems, but it's 62.4 or 0.3. Most of them are acceptable. Pounds per cubic feet. How do we calculate the pressure though? Your pressure is going to be your gamma multiplied by H of C. The centroid of that, H of C, is going to be the depth at this location. 4 gamma multiplied by 4 multiplied by the cross-sectional area is going to be the area of a circle, pi r squared, right? If you look at it from the side, you're going to see a circle, right? That's it. You have the forces in all directions. Yes. That's gamma of water in the in English units, in British units. That that will, I mean, I will always give it to you in an exam, or but it is not a bad idea to just memorize that. Can anyone tell me what is the gamma of water in SI? Gamma is rho G, right? What is the gamma of water in SI? The density of water in SI, does anyone remember that? We usually make an assumption here, use a number. It's a very 1,000 kilograms per cubic meters, right? And what about the gravitational force? 9.81. You have your answer. This is actually very, very important. You just have to make sure you know gamma is rho multiplied by G. Because I've seen other students in like future classes that don't know this, and because they don't know this, they will get confused. But outside of this class, no one's gonna use gamma for rho G. They will always use rho G, right? Okay. If there's no question, then let's move on to the next. Let's move on to the next. We are moving fast today. Let's move on to the next example problem. Let's see. I'm gonna ask you guys to solve this example problem. And whoever submits an answer in like 10 minutes, because we are moving so fast, I think we have enough time, will get a bonus point, okay? It is essentially the same problem, the same idea as this problem. You wanna find the forces on a curved surface. And for those of you who are watching this online, there are a lot of students who are watching this online. You can actually send me an email in 10-15 minutes. That will, I will give you the bonus points as well. Okay, so this is the problem. We have an 18 feet long lightweight gate. This is the figure. This is your gate. Okay, and this is the surface of water. So this gate is holding the water. Is a quarter circle and is hinged at H. You want to determine the horizontal force P that we have to apply here to hold the gate. We essentially want to find the force P that is required for us to hold the gate. Okay. And let me see. You need gamma of water, of course, 62.4 pounds per cubic feet. And what else do we need? I guess that's it. The radius here is 6 feet. And it's a lightweight gate, so the weight of the gate is negligible. And also the friction at the hinge is also negligible. So I want you to find the force P required to yes, 6 feet. 6 feet. Of course, the first step, I'm going to tell you what the first step is. The first step is to take out the curved section and draw a free body diagram for that curved section. Right, you have the force P that you want to calculate, and you have the hinge here. You don't need to give me final number, just give me like a solution method, right? Just want to make sure that you are not thrown off. In your free body diagram, you don't need to include P, right? Just to make sure that you are not thrown off. We are essentially want to calculate the force imbalance, which is going to tell us how much P we need, right? Okay, do we have anyone? There's no brave. So you don't need to come to the board. Just give me your answers. No one? Okay. Okay, so let's see. Let's solve the problem. What are the forces that are present here? The first one is going to be, the first two are actually going to be your vertical force that is being exerted by the gate to this body of water, the vertical force, and the horizontal force, right? And we also have the force that is being exerted by the rest of this water, this body of water, right? Let's call that F1. What else do we have? We have weights. And that's it. Do we have any other forces here? No. Okay. So sigma F in x direction is going to be equals to 0, which means that your horizontal force is going to be equals to the force of this body, which is going to be equal to pressure at the centroid multiplied by A. Right? And sigma F in y direction is going to be equals to 0 as well, which means that F of V is going to be equal to W, or gamma of water multiplied by the volume. Okay, what is this PC here? How can we calculate this P of C? It's going to, if you recall, from the earlier discussions we have had, it's going to be equals to gamma multiplied by H of C. So pressure that is being applied to the centroid of this line, right? So this is gamma HC A. A here is the cross-sectional area of this, right? Whatever that is. It's going to be this length multiplied by the width. It is perpendicular to the board. It is 18 feet. Right? It was given to us. It is 18 feet in this direction, right? So your A is going to be 6 multiplied by 18. H of C is going to be the centroid of this, which is 6 divided by 2. And gamma is 62.4. H of C is the centroid location, not the location of center of pressure. Just have to make sure not to confuse those two. So what is this value? 62.4 multiplied by 3 multiplied by 6 multiplied by 18. It is eventually going to give you 20,200 pounds. Okay. We should do the same analysis for the vertical force in the other direction for weight. What is the volume of this body of water? How can we calculate this volume? It's going to be the surface area, this surface area, multiplied by the width of this gate, right? The surface area is pi r squared divided by 4, because it is a square of it is 1/4 of a circle. And then, so we're going to get 62.4 multiplied by your pi r squared, which is 6 feet, divided by 4, multiplied by 18. If you do this calculation, your F of V is going to be 31,800 pounds. Okay, so we have the forces in each direction. How can we calculate the force P here? The force P that is needed to hold the gate. So the force P is being applied to the gate, right? So let's draw the free body diagram of the gate this time. Not of that body of water, but the gate, right? We have a horizontal force in this direction, right? That is being applied, and a vertical force in this direction, and a pressure force in this direction. The idea is this pressure has to be able to hold the gate, right? So what condition should be met here? The moment these two forces are creating has to be equal to the moment that the pressure force is calculated. So your sigma m has to be equal to 0. Okay? But we know what is the arm of this force, right? The moment on this hinge has to be 0. Let's call it sigma m of O, right? Or m of h, whatever you want to call it. The arm of this force that is creating the moment is going to be 6 feet. So P multiplied by 6 has to be equal to FH multiplied by its arm. Let's call it X1. FV multiplied by its arm. Let's call it Y1. And let's just make sure we are correct on the directions, FH and FY, right? The directions are correct. Okay, so P multiplied, yes. Why do I feel like someone's asking a question? So the next step is to find X1 and Y1. But how should we find that X1 and Y1? The idea was the resultant forces pass through the center of pressure, right? Remember that? We had XR and YR, right? So the arm these forces have to create that moment is actually the distance center of pressure has from this hinge, right? And if you recall, we had the equation for center of pressure for the 2 points that identify the center of pressure as y of c plus I, the moment of inertia, divided by a multiplied by y of c. That was 1. And the other one was x of c plus I of xy divided by a multiplied by y of c. Okay, x of c here is 0. The location of centroid in the x direction is going to be 0, right? Because because this force is being applied. The centroid of this is going to be 0 because we are starting from this coordinate system that is start from 0. So it's in the same plane, x sub c is going to be 0. So we are going to be left with the moment of inertia, area, and y of c. What is the moment of inertia for this body? It will be given to you. I'm going to just write it. I of xc, that's xc. And this is I of xyc, xc. Okay. I of xc is just going to write it down for you. But this will be given. I of xc is 0.05 8 pi r to the fourth, and I of xyc is negative, there's no pi, that was my mistake, negative 0.0164 r to the fourth. We have the location of y of c, which was 3 feet, right? We can calculate the area. Just plug all of the values in. Your x1 and y1 are going to be equal to, for xr or x1, doesn't really matter, is going to be 8 divided by pi feet. For yr, which is equal to this y1, it is going to be equal to 2 feet. These are the arm of these forces that are creating the moments on the hinge. So we have everything we need. We have f of h, we have f of v, we have x1, we have y1. Just plug in the numbers and you will be able to find the force P at this location. Is going to be equals to 20,200 pounds. Is there any questions? Okay. So let's move on to another example. For this example, we are going to focus on the motion, the rigid body motions we talked about. If you recall, we talked about the linear motion and rotations, all for the rigid body motion. Essentially, a container of fluid can either rotate around center of rotation or can move altogether. And this is the problem. This problem is going to focus on that. This problem is a little confusing, if you will. Can get a little confusing. So make sure you follow all the steps. And if you didn't understand one part, or some part wasn't clear, make sure to ask your question. So we have a tank of a tank has a height of 5 centimeter and a square cross section measuring 5 centimeter on the sides. So we have this tank, which is 5 centimeter, and it's of course a 3-dimensional thing. Okay, 5 centimeters on each side. The tank is 1/3 full of water. So 1/3 full of water. And is rotated in a horizontal plane with the bottom of the tank 100 centimeters from the center of the rotation and 2 opposite sides parallel to the ground, which essentially means that we have rotated this thing, this tank, and it is rotating around an axis that is 100 centimeters away. Okay, does this make sense? The gravitational force is in this direction. So essentially, if it wasn't rotating, the water would spill out, right? Because of the gravitational force. And it is 100 centimeters away from the bottom. So 1 meter away from the center of rotation. We want to find the maximum rotational speed that the tank of water can be rotated with no water coming out of the tank. Is this clear? So you want to rotate this in a way with a speed that essentially prevents any water coming out of the tank because of the gravitational force. Right. So if you start rotating it, it will be like this, right? That this will be the water surface, the new water surface. Okay. And then if you rotate it with enough speed, nothing will come off because of the forces, right? The centrifugal forces that are acting in the opposite direction on water. Is the premise of question clear? Do you understand what the question is? Okay. So the first thing we need to do is to go back to the rotational motion that we had and write this equation. If you go back, you see for a rotational motion, we had this equation, rho g dz plus rho gamma squared dr. Changes in pressure. From previous lecture, I assume you remember that on a free surface, pressure is going to remain the same at each part of that free surface. Okay, so dP, or the changes in pressure on that free surface, is going to be 0. So 0 is going to be negative rho g dz plus rho gamma squared r dr. Okay. You can divide everything by rho as well. Make it even simpler. And then we can integrate. If you integrate, your z is, you're going to have integral of, we can take the g out. Z is going to be called dz plus omega squared integral of r dr. Can we take this integral? That's the first question you need to answer. Let me actually give you the dimensions here as well. We have b and we have h. And this is going to be r of L. So for R, this is in the R direction, this is in the Z direction. So for R, we are taking the integral from R of L to RL plus H. If you want to have a final solution. And for Z, what we can do is to start the coordinate system from this middle here, but you can start it from anywhere. Doesn't really matter. Then we are taking the integral from this location, negative b over 2 to b over 2. Okay. If you take this integral, what's going to happen is that you are essentially going to prove that this is everything is equal to 0. You're not going to find anything. That's why you have to go a little deeper, actually. Let's magnify this part. This is, let's say, this is the surface of the water. What we are going to do, instead of taking the integral from negative b2 to b2, we are going to take the integral from negative b2 to a random location z to find the equation of that line, and from RL to a random location R. So this is going to be your R. This is going to be your Z. So let's take this integral. It's going to be negative G multiplied by, we are going to get Z from negative B2 to Z plus omega squared R2 R squared divided by 2 from RL to R. So plug the values in, and we are going to get negative B2, it's going to be negative G, Z plus B over 2 plus omega squared R squared over 2 minus RL squared over 2. Which essentially is giving us the equation of the constant pressure line. Just play with it. Let us do this. Let's do this. Let's divide everything by G first. So we're going to get Z plus B over 2 equals to 0 by negative G, negative omega squared divided by G. Then we can take these 2 out as well. So divided by 2G RL minus R squared. We can actually take this negative inside as well to make it R minus RL squared. And eventually move everything to the other side. So Z is going to be negative B over 2, negative omega squared 2G R minus. So we have the equation of the line for the free surface. Okay. Well, how is that going to be beneficial to us? How can we make sure that we are avoiding or preventing any water spilling out of this container with rotating it fast enough? Okay. Or how can we find that specific angular velocity needed to prevent the any water spillage? Okay. We have the equation of this line, right? The free surface line. Okay. What should we do then? What should we do? What is the next step? Just think about it. What happens here if you don't have any water spilling out? What will happen to the volume of that water? Is the volume of the total volume of the bottle, is it going to change at all? No. So if you can calculate the volume in this condition, and then can calculate the volume in this condition, and set them equal, they will be essentially, we'll be getting somewhere, right? Okay. Let's do that. What is the volume? What is the volume of a non-rotating container? It said it was 1/3 full. The container was 1/3 full. So the volume is going to be the total volume of the container, which is this multiplied by this multiplied by this, divided by 3, right? Which is going to be BH squared divided by 3. Okay, but what is the volume in this condition? What is the volume in this condition? How can we find the volume in this condition? The volume in this condition is going to be, so this length is going to be constant, right? This length, the water will be, right? Let's call that B. That B will be there. And then Z and R are changing. We don't know them, right? Let's just B multiplied by a combination of Z and R. Okay, so essentially what we are dealing with, let's say this is a ZR plot, and this is something like this. We want to find the surface area underneath this curve, right? That is multiplied by the width of this, whatever that is. How can we find the surface area underneath this curve? Just have to take the integral, right? So to find the volume, we have to take the integral B multiplied by the integral of ZdR. Do we have Z as a function of R? Yes, we do. And this Z is changing from negative B2 to B2 here. So B multiplied by the integral of negative B2, B over 2 minus omega 2G, R minus R of L, squared, dr. Okay, that's actually that has to be the changes in R. So R is changing from this location to this location. Sorry, RL plus R. So essentially 95 centimeters to 100 centimeters, right? We were given this. And as long as that equation is true, we are keeping all of the volume of the water inside that container, meaning that there is no spillage. I assume you can take this integral yourself. That's the integral is going to be BR divided by 2 minus omega squared over 2G, R to the third divided by 3 minus R multiplied by RL squared, right? And then that changes from RL 100 to RL plus H. which is 95 centimeters to 100 centimeters. Okay. So that's it. We just plug in the numbers. And it will give the only unknown here is going to be your omega. You should be able to find the omega. Is this clear? There is one assumption we made at the beginning of the solution. That was essentially the assumption we made was that the surface starts from here, right? Because we are looking for the rotational speed that is needed to keep this in, right? We don't want a rotational speed that is higher than that. So surface can start from here. It doesn't need to start from inside, right? But this surface could have gone actually to this other wall, right? We made the assumption that the surface remains on this wall, right? To be able to find that parameter. But this is an assumption you can always make, right? And there is a check for that assumption. We are not going to go into the details of it. Okay. Is there any questions? Yes. It was given to us. Didn't I say that? It was given to us. Okay. I had more questions that I want to solve for you, but I guess we have to stop here. And if we were at the, like before the exam, if we were far enough into the course material, then we will spend one lecture on just solving exam problems, right? To make sure that you are clear. But if not, I will try to record an example problem, like solution session at home, and just post on YouTube or Blackboard, so you can have access to it. And hopefully you don't have any, like, there is no confusion or anything. And don't forget that your homework 2 is posted. It will be due next Thursday. It has 11 questions. The 11th question is just a bonus question, which can take up to 25% of a homework grade, meaning that it will be 0.75% of your total grade. Okay, so it won't be added to your homework grade. It will be separate, right? It will be added to your bonus points column. And yeah, I guess that's it. Have a good weekend.